morning. I am Dr. Ravi M. Edahalli, Professor and Head of the ENC Department, SG Balekundri Institute of Technology, Belagavi. So, we shall continue the discussion on the bipolar junction transistor. In the last class, we have seen the transistor current. As this particular slide shows, we considered a PNP transistor, right. If we apply the Kirchhoff's current law, we get emitter current is the summation of the base current and the collector current. And also we know that alpha DC is equal to IC by IE, that is output current, by the input current, that is collector to emitter current. Alpha DC, it is called as common base DC current gain. Therefore, IC, the collector current, is equal to alpha DC times of emitter current. If we substitute this, the equation for IE into equation into 2, so what we will get? So, therefore, IC is nothing but, right. So, alpha DC divided by 1 minus alpha DC into IB here. So, therefore, if we replace alpha DC by 1 minus alpha DC by beta DC, we get IC is equal to beta DC times of IB here, where beta DC is called as common emitter DC current gain. So, friends, we have derived the relation between the beta DC and alpha DC, and also we discussed about the configuration of bipolar junction transistors. As I told you that the two port networks are having two input ports and two output ports. In order to use the BJT in a two port network, we need to have one common terminal, because BJT is having 3 terminals. So, therefore, one of the terminals of the bipolar junction transistor has to be made common with reference to both input and the output. So, that is how it results in 3 configuration of bipolar junction transistors. So, therefore, we get common base configuration, then common emitter configuration and common collector configuration of BJT. Here you can see that this is particular configuration is common base configuration of bipolar junction. Here you can see that the emitter is the input and collector is the output here. Whereas this second slide, this particular figure shows the common emitter configuration of BJT, where emitter is common with reference to the base, that is the input, and with reference to the collector, that is the output here. We have got one more configuration of the BJT, that is common collector configuration here, wherein the collector will be the common with reference to the base, that is the input, and with reference to the emitter, which acts as the output here. Also, we discussed about the input characteristics of the common input and output characteristics of the common base configuration. So, friends, you know that here the input characteristics, it is the plot of graph between base to emitter voltage to the emitter current here. So, VBE is the input voltage, IE is the input current, keeping VCB, that is as a constant here. So, if you can able to write for a constant fixed value of VCB, if you draw the plot of VBE versus IE, you will get input characteristics of the common base configuration here. From this, it is very much evident that the VBE, until it reaches the threshold voltage, it is also called as the cut-in voltage, which is the 0.3 volts for the germanium transistor, 0.7 volts for the silicon transistor. So, the current will be 0 here. So, once the VBE crosses this particular cut-in voltage, then current will start rising through the device. So, the other thing what you can note on this, the input characteristics of the common base configuration, it is almost looks similar to that of the forward biased PN junction here. So, the third conclusion what you can derive from this is that whenever for a fixed value of VBE, as the VCB increases, correspondingly IE will increase here. So, that means in the last class I told you for 0.8 volts of VBE here, right, whenever VCB is increased from 1 volt to 20 volts, correspondingly you can see that the IE also increases here. The reason, because the VCB is the voltage, reverse bias voltage applied across the collector to base junction. As the reverse bias across the collector base junction increases, the width of the depletion region existing across the reverse bias junction increases here. Therefore, the depletion region, it penetrates more into the base region and thereby reduces the base current here, that is recombination current, and in turn it increases the collector current, and therefore, since IC is IE, so therefore IE will also increase here. And also we have discussed about the output characteristics of the common base configuration here. So, the output characteristics, it is the output voltage versus output current, keeping the input current constant here. So, output voltage is VCB here and output current is IC here, and the input voltage is the IE here. So, you can note that note from the output characteristics of the common base configuration, there are three regions are there. One is the cutoff region, another is saturation region, and third is the active region here. The cutoff region is the region below the current curve IE equal to 0 milliampere. So, this is called as the cutoff curve here, and this whatever you can see the right in the blue color to the left of the VCB equal to 0, that region is called as the saturation region, and the region between that of the cutoff region and saturation region is called as the active region. And also you can note that the collector current, it is independent of the variation in the VCB. That means, in spite of variation, right, irrespective of the variations in the changes in the VCB, the collector current is remaining, that is constant here. So, therefore, you are getting a flat curve in the active region, and this is because of this flat nature of the curve. So, therefore, active region is being preferred for the amplification purpose. And another point, you know that, so active region, why it is being preferred, because we have a flat curve, that is linear region. The second point is that, so there is a equal distance exists between these two curves, and that is very much required for the faithful amplification. So, another point you can note down, that once the VCB increases beyond 25 volts, there will be a breakdown here, right, breakdown that results in the a large increase in the current, collector current. It is because of the fact that the depletion region across the collector base junction, it almost reaches the depletion region along the input junction, that is emitter base junction here. And the third point what you can seen from this curve is that even at VCB, when VCB is made 0, right, the collector current is not 0. There is a finite value is there for corresponding to VCB equal to 0 here. So, it is only because of the fact that, because as you know that even under the no bias condition, there will be a depletion region exist across the PN junction, and this PN junction will allow the flow of the current across that here. So, therefore, when this VCB is reduced to 0 here, the collector current is having some finite value. So, therefore, in order to force this collector current to 0, what we need to do? We need to write the reverse, the polarities of the reverse bias applied across this. That means, we need to forward bias the collector base junction there. So, once we the forward bias the collector base junction here, the depletion region whatever that exists across the collector base junction, it will repel the minority charge carriers, and therefore, the current, that is collector current, ceases to 0 here. And in this particular session, we shall try to understand and analyze the two characteristics, that is common emitter characteristics of the BJT and common collector characteristics of the BJT. And at the end, we shall compare with the other configuration. as the name indicates, the common emitter configuration, it is called so because the emitter is common to both input and output terminal. Since it is common emitter, here please note that the base acts as the input terminal, whereas the collector acts as the output terminal. And since emitter is common with reference to both the base and collector terminal, it is called as the common emitter configuration. And also the emitter, it is usually at a almost close to or at the ground potential here. And one more point you can note on that, the almost amplifier design is using connection of the common emitter configuration. It is mainly due to the fact that high current gain and high voltage gain here. So, this common emitter configuration compared to other two configuration, that is common base and common collector, it is having high current gain as well as the high voltage gain. It is due to this fact. So, for amplifier design, this particular common emitter configuration is being preferred here. In order to explain or describe the behavior of the common emitter configuration of the BJT, we need to study two characteristics. One is the input characteristics, other is the output characteristics. So, now this particular slide shows you the NPN transistor that is biased in a active region, and similarly PNP transistor biased in active region. So, in this case NPN, the upper N acts as the collector and the middle layer P that acts as the base here, and the bottommost N layer it acts as the emitter here. So, please note that emitter is common with reference to the B here, that is base, that is the input, and also with reference to the collector which acts as the output here. Similarly, in this PNP transistor, the upper P acts as the collector, that is the output, and lower P acts as the emitter, which is common with reference to the base, that is the input, and the collector, that is the output here, and the middle layer N layer, it acts as the base layer here. So, from this we write, if you apply the KCL, we can note that the emitter current, it will be a summation of the collector current and the base current, because the emitter current, it is the outgoing current, and in this case the PNP, and IB and IC, that is base current and collector current, are the incoming current. So, therefore, the I is nothing but IC plus IB here. Now, let us discuss the input characteristics of the common emitter transistor here. So, input characteristics means it is a plot of VB versus IB keeping VC constant here. So, you can note that this plot of the input characteristics of the common emitter transistor, it almost looks similar to that of the forward biased PN junction here. So, therefore, until the VB reaches a certain value, the current will be 0. Once it exceeds that value, there will be a large current, there will be a current starts flowing through the device here. So, therefore, and the another point is that, so for a given value of VBE, if you note on this, so given value of VBE, you can see that, Now, let us assume that for given value of the 0.7 volts, for fixed value of 0.7 volt, if I extend this line onto the characteristics, you can extend along the y axis here. You can see the intersection point between the character and this. If you can extend, what you can observe is that for a given value of the VB, that is 0.7 we have volts we have taken, whenever the VC increases, from the 1 volt to 20 volts, what happens to the IB? IB will decrease here. That is what you can note on here. So, therefore, I repeat. So, for a given value of VBE, that is a constant fixed value of VBE, whenever the VCE increases from 1 volt to 20 volts, correspondingly the base current decreases. So, that you can see from this particular slide here. So, therefore, it is mentioned that for a given value of VBE, IB base current is reduced when higher values of VC are employed here. And please note that, so IB will flow only when VB becomes equal to 0.7 volts, which is the cut-in voltage for the silicon transistor, and 0.3 for the germanium transistor here. And let us see now the output characteristics of a common emitter transistor. Common emitter transistor means the emitter is common with reference to both input as well as the output here. In common emitter configuration, input is the base and output is the collector here. As shown in this figure, okay, there are once again there are three regions are there. One is the cutoff region, active region and saturation region here. So, cutoff region is the region below the curve of IB, that is base current equal to 0 microampere. So, this region whatever shaded region is there, that is nothing but the cutoff region here. So, and we have a saturation region, that is to the left of the VC equal to 0, whatever shaded region here we have got now. So, that region, okay, is called as the saturation region, and the region between that of the cutoff region and the saturation region, it is called as the active region. What is the main feature of active region? So, linearity. Here also please note that the curves are almost so linear in nature. And another point is that compared to the common the common base transistor, you can note that, so these curves in the active region they are having a slope. So, slope is more pronounced in the output characteristics of the C transistor compared to that of the CB transistor, the CB configuration there. The reason is because here you can see that, so whenever for the VC increases, you can see that, okay, what happens, the collector current it will also increases here, but it is having a more pronounced slope compared to that of the output characteristics of the CB configuration here. And also you can note that at this knee voltage, so what is the voltage? It is VCE is equal to, okay, you can note on that this is nothing but VCB, okay, that is VCB, okay, plus what it is nothing but VBE. So, therefore, what you can see that VC is nothing but VCB plus VBE here. At this knee voltage here at this point, okay, this VCB will be 0 here. So, therefore, further reduction of VCE, what happens? It will forward bias the collector base junction, and therefore, the collector current will reduces to 0 here. So, that point you can note on here. And so, now, let us see the three reasons of the output characteristics of a common emitter configuration of a BJT. As you have seen, the active region, in the active region the input junction is forward bias, whereas the output junction is reverse bias, that is input junction is base to, that is emitter junction, that is forward bias. So, and the collector to base junction, it is a reverse bias here. So, similarly here this active region is being preferred for the amplification purpose, whereas the saturation region, in saturation region input junction and output junction both are forward bias, this particular region is being preferred for for a switching operation, whereas in the cutoff region there is no conduction of current, only a small leakage current flows, and also you can note that both input and output junctions are reverse bias here. And also let us see the DC current gain of beta DC, that is called as beta DC here, that is the common emitter, okay, DC current gain. So, therefore, it is called as current gain. Current gain means it is the ratio of output current versus the input current here. So, in common emitter the output current is collector current and input current is the base current. If you take a ratio of this output current and input current, so that gives you the beta DC value. So, here you can note that the IC and IB are determined at a particular operating point, that is called as the Q point, or in that is quiescent point. Quiescent means that is silent point, that represents the operating point of the BJT here. So, please note that the beta DC, that is common emitter DC current gain beta DC, it ranges from 30 to 300 for a transistor 2N3904. And also, if you go through the data sheet of the or manufacturer specification of the transistor, the beta DC it is mentioned as HFE. F is capital, E is capital, and with H is derived from AC hybrid equivalent circuit, and FE are derived from forward. So F stands for forward, that is forward current amplification, and E stands for common emitter configuration respectively. So therefore, usually in the specification sheet or manufacturer specification sheet, the beta DC is mentioned in terms of the HFE, where H is derived from AC hybrid equivalent circuit, and FE, capital letter FE stands for, F stands for forward current amplification, E stands for the common emitter configuration here. Apart from the common emitter DC current gain, we have one more current gain, that is called as common emitter AC current gain, or in short it is called as beta AC here. So as I told you that current gain is the ratio of output current to the input current. So here, as I told you that output is the collector current, whereas the input is the base current here. So therefore, AC beta or the common emitter AC current gain, it is defined as the ratio of the changes in the collector current to the changes in the base current here. Therefore, and where IC and IB are determined at a operating point here. And please note that on the data sheet, so beta AC, that is called as common emitter that is AC current gain, is mentioned as HFE. FE is small letter, right, whereas beta DC it is mentioned as HFE also, but where FE is in capital letter there. And you know that usually to operate BZS amplifier, we prefer the common emitter configuration. It is only because of the reason that this will provide more current gain as well as the more voltage gain. And also it should be noted that to operate the BZT in as an amplifier, we make use of the active region, where the output characteristics are linear in region, and the there is a equidistance, the equal distance exists between the neighboring curve here. So which is very much important as far as the faithful amplification is concerned here. Now let us see the relationship. Let us derive what is the relationship between the common base current gain, that is alpha, that is or it is also called as alpha DC, and beta, that is called as common emitter the DC current gain here. So you know that the emitter current is nothing but sum of the collector current and the base current here. So therefore, if you substitute the equation IC into beta IB into 1, what we will get? I is nothing but so beta 1 plus IB here. So what we are substituting here, in case of you are substituting IC is nothing, right, in terms of beta terms of IB here. So therefore, what will get? I is equal to, if you take IB common in the bracket, I will be left with the beta plus 1 here. So the also we know that the alpha is nothing but that is common base current gain, common base the DC current gain is defined as the output current by the input current, that is collector current by the emitter current here. So therefore, from this you can say that I is nothing but IC by L. So that you can assume it as equation 2 here. Similarly, we know that beta is what? The common emitter DC current gain, which is once again a ratio of the output current by the input current, but in common emitter the output is the collector, that is collector current, and input is the base current, and from this we can say that IB is equal to IC by beta. This you can assume it as equation 3. If you substitute equation 2 and 3 in equation 1, we get alpha is equal to beta by beta plus 1, and beta is equal to alpha by 1 minus alpha here. And please note that for any BZT, the common base current gain, it ranges from 0.9 to 0.998. If I substitute this, so we will get beta in the range of 40 to 50. Therefore, what you can say that the beta will be having more higher value compared to the alpha here. That means the common emitter current gain it is more than the common base the current DC current gain here. Now let us consider the common collector configuration here. So here in this particular slide shows you the PNP transistor. As I told you, this is a common collector configuration. The collector acts as a common terminal between the input and the output here. Here the input is the base, that is the N layer, and the output is the P layer, that is the emitter here. So therefore collector, it is common, right, it is shared between the input, that is base, and the output, that is the emitter here. Okay. So and also you can see that the N, this is we are using a PNP transistor. Okay. The input junction is forward bias. So how? By connecting N layer to the negative terminal of the VBB with reference to the collector. Similarly, okay, the emitter, it is emitter collector junction is reverse bias by connecting P layer, right, or emitter to positive terminal of V with reference to the collector here. Similarly, in case of NPN, you can see that, okay, we have NPN layer there, okay, and NPN with 3 terminals, that is emitter, base, and collector here. And since it is a common collector configuration, the collector acts as the common between the input, that is base, and output emitter here. So therefore you can see that the collector is the it is shared between the input as well as the output here. And apart from that, you can see that the input junction, that is base collector junction, is forward bias by connecting P layer to the positive terminal of the VBB with reference to collector. Similarly, the emitter collector junction is reverse bias by connecting the emitter to the negative terminal of VE with reference to the collector here. This is the symbol of PNP transistor in case of common collector configuration, and this is the symbol of the NPN transistor, okay, using common collector configuration. Friends, you know that this common collector configuration, it is also called as the emitter follower, or sometimes it is called as the voltage follower. Emitter follower or voltage follower, it is only because of the reason that the voltage gain of this, okay, common collector configuration is 1, okay, whereas the current gain is on the higher side. So therefore, and the input impedance is very, very high and output impedance is very, very less. It is because of these 4 features. So the common collector configuration is called as the emitter follower, and it is being used as, okay, the impedance matching device here. So emitter follower means it is also called as the emitter, because here the output is taken at the emitter and which will follows the input, right, that is the base. So whatever changes that take place in the base, so same changes are going to take place in the emitter. So therefore this okay, common collector configuration of BJT is called as the emitter follower here. So here once again it is a common collector configuration because the both signal source and load share the collector terminal as common connection point, and output is usually obtained, it is obtained at emitter terminal, that's the name emitter follower there. So common collector configuration of BJT, it is provided with a load resistance connected from emitter to ground here. So it is being used primarily for impedance matching purpose, only because of the fact that it is having very high input impedance, very low output impedance, and voltage gain is 1 and current gain is very high. So it is because of these 4 parameters. So that is impedance matching device, why it is being used, because the input impedance is very high, output impedance is low, and voltage gain is 1 and current gain is it is on the higher side here. Now let us look into the input characteristics of a BJT in common collector configuration. So this is the plot of the VCB versus IB, right, keeping VCE constant there. Okay. So here you can see that VCB is what, the input voltage, because this is the common collector configuration. So collector is common with reference to both input as well as the output here. So therefore in this case the VCB acts as the input, whereas the IB acts as the input current. This is input voltage and this is the input current. So it is a plot of input voltage versus input current keeping output voltage constant, that is VCE here. So we have plotted, right, what is being done for a fixed value of VCE, that is 2 volts, right, will increase the value of VCB and corresponding value of IB are noted down, recorded, and same thing is plotted on the graph sheet here. Similarly, the same procedure is being repeated for VC equal to the 4 volts here. And please note that this common collector input characteristics are quite different from both the CB as well as the CE input characteristics here. it is unlike, because you have seen that the common emitter as well as the common base, the input characteristics, it is almost similar to that of the forward biased PN junction diode, the characteristics of the forward biased PN junction diode. However, in this case, the input characteristics of BJT in a common collector configuration, it looks totally different from the either CB, that is common base configuration, or common emitter configuration. The difference, it is mainly due to the fact that VBC is largely determined by VEC there. So, VBC or VCB, that is one and the same. This VCB, it is mainly determined by VEC here. Now, let us see that, okay, how it is determined. Now, in this particular figure, you can see that VEC is nothing but what? It is VEB, okay, plus VBC here. Okay, if we add VEB and VBC, you will get VEC there. So, from this equation, you can say that VEB equal to VEC minus VBC there. So, therefore, whenever this input voltage, VBC is what? Input voltage increases, okay. What happens here? What happens to VBE? That is will decrease, because this is having a negative sign there. So, whenever there is an increase in the VBC, which is nothing but the input for the input voltage for the common collector configuration, so the VBE will decrease here. So, when VB will decrease, so therefore, here you can see, just that is what I can note down here. So, this is right, whenever if I want to increase this, okay, VBC here, so VEB will decrease here. It is only because of the fact that, so a negative sign attached to VBC here. So, when VBE decreases, naturally what happens to IB? IB will decrease. So, therefore, okay, IB is getting decreased here. So, therefore, here you can see that, that is VBC, I am increasing VBC there. VBC is nothing but when VBC increases, so VBE will decrease. Okay. When VBE decreases, so what happens here? The IB will decrease here. So, therefore, you are getting the plot in this particular fashion here. So, here you can see that whenever VCB increases, so correspondingly VBE will decrease. This decrease in VBE, right, it will, okay, reduce the IB, that is base current, and therefore, you will get this particular plot here. So, now let us see the output characteristics of BJT, right, in a common collector configuration here. Okay. So, the output characteristics, it is a plot of what? The output versus the output voltage versus output current here. So, in this here, in this configuration, it is a common collector configuration. Base is the input and collector is the output here. Therefore, output voltage is VCE, output the current is the IE there. So, here common collectors, in the common collector configuration, base is the input, emitter is the output here. Therefore, output voltage is what? Here the output voltage is, in this case, output voltage is what? The output voltage is the collector to emitter voltage, and output current is emitter current here, keeping the base current constant here. I repeat here, the output characteristics is a plot of, right, the graph between the VCE versus IE, or this is output voltage, VCE and output current here, because this is a common collector, no, common collector configuration. What is the input here? Input is the base, output is emitter. Therefore, output voltage is VCE, output current is the IE here, keeping the input current, that is base current, constant here. So, what you can note on from this? Okay, one thing is that, okay, so this CE output characteristics are plotted, right, VCE versus or against IC here, because IC approximately equals to IE. The CC output characteristics are practically identical to those of CE there. So if you compare the output characteristics of this common collector configuration with that of the common emitter configuration, right. So you can say that since IC is approximately equal to IE, so this output characteristics of the common collector configuration, it looks similar to that of the common emitter configuration, that because IE, you know that IE is what, IE is equal to IC plus IB. IB is it is in terms of microamperes, it is negligibly smaller. And this particular output characteristics of the common collector configuration of the BJT consists of once again the three region, that is, one is active region, then cutoff region, then saturation region. The cutoff region, it is defined by this shaded region, wherein wherein here you can see this is the region, this called as the cutoff region, that is the region below IB equal to 0 microampere. That region is called as the cutoff region. In this region, very almost no conduction of current take place, or it is only a leakage current will be flowing. And this region, whatever shaded region is there, right, to the left of VC equal to 0 here, this is VC equal to 0 point. So this region is called as the saturation region, and the region between the saturation and active region, it is called as the active region there. And another thing what you can note on is that here you can see that when VC increases, what happens here, the IE will also increase here, right. So therefore this particular case output characteristics have got pronounced slope compared to the other here, because compared to this you can see that whenever the VC increases, so what is happening, the collector current is also slightly getting increased for a for the constant value of base current here. At this point here, what you can see that once again at this point knee voltage, once again here VCE is what, VCB plus VBE here, and at this knee point VCB will be 0, and therefore further decrease of VCE will increase will forward bias the collector base junction, and therefore the emitter current becomes 0 here. So that is what you can note on in this case. So if you compare these three configuration, that is common collector configuration, common base configuration, and common emitter configuration, these are the few differences we are getting. One is the phase relation between the input and output. In case of the common emitter, it is 180 degree phase shift we are getting between the input and output, whereas in both common collector and common base it is the 0 degree, that means there is no phase shift here. In case of common collector, what is the input terminal? It is base. Input terminal in case of common base it is emitter, in case of common base it is emitter, in common emitter it is base here. Whereas the common terminal in case of the collector, it is nothing but, so here you can say that it is emitter in the case of the common collector, and output terminal it is collector in case of common base, and output terminal it is collector once again in common emitter here. As far as the voltage gain is concerned, the common collector, it is instead of, you can say that low, usually it is 1 here, unity gain amplifier, and whereas the voltage gain it is on the higher side in the common base, whereas the common emitter configuration is having the moderate voltage gain here. Whereas as far as the current gain is concerned, it is very high in case of the common collector configuration, it is very low in case of the common base configuration, whereas once again the common emitter configuration is having moderate or medium, that is in between that of the common collector and common base configuration there. So that is the reason. So if you know that, the power gain, if you compare once again in power, for common collector it is medium, for in case of the common base it is low, and it is high in the case of the common emitter here. So if you compare the input resistance, you can see that it is very input impedance is very high in common collector, and output resistance is very low in case of the common collector compared to other the configuration here. So, what is the conclusion is? Conclusion is that what, right, the common emitter configuration, it is being preferred, right, as an amplifier. It is only because of the reason that this common emitter configuration is having moderate value of voltage gain as well as the current gain, and input resistance is medium, output resistance is also medium. Whereas common collector configuration, it is being preferred as for the purpose of impedance matching device. So, it is only because of the reason that it is having unity voltage gain, very high current gain, and input impedance is very high and output resistance is very low there. So, now let us conclude the this particular session. So, friends, we have seen that, okay, we have studied and analyzed the input and output characteristics of CE configuration here. So, from this CE configuration input characteristics, it is input voltage versus the output the input current, that is VB versus IB, keeping output voltage constant here. Okay. So, another point is that the input characteristics looks almost similar to the forward biased junction of the PN junction, forward biased PN junction. Okay. The another point is what you can note on that, for a constant or fixed VBE, whenever VCE okay, increases, IB will decrease. Okay, that's point you can note on. The third point is that until VB reaches the threshold voltage or cut-in voltage, so there will be no current flowing through the device here. Once it exceeds the cut-in voltage, so current will start flowing through the device. And as you note, right, as you know that the cut-in voltage or the threshold voltage, it is 0.3 volts in case of germanium and 0.7 volts in the case of the silicon here. And also we studied about and discussed about the output characteristics. This output characteristics has got three regions. One is cutoff region, that is below the current curve IB equal to 0 microamperes, and the saturation region, that is to the left of the VC equal to 0 volts, and the one more is active region, that is between that of the cutoff and active region. And please note that active region is being preferred for the amplification purpose, whereas the cutoff and saturation region are being preferred for, right, whenever the transistor is operated as a logic switch. And once again you can note on that, okay, whenever the VC increases, you can see that, okay, IC will slightly increases, that is why you are having a small slope here. Okay. And at this knee point, okay, that means whenever VC decreases, okay, at knee point the VCE is nothing but what, VCB plus VBE, and VCB becomes 0, that is a voltage reverse bias applied across the output junction, and further reduction of VCE will forward bias the collector junction, and therefore the collector current becomes 0 there. And also we could able to establish the relation between the alpha and beta, and we have seen that the emitter current is nothing but the IC, that is plus IB here, and we know that, okay, IC in terms of the beta is, that is IC equal to beta times of IB here, and if you substitute, right, so this IC into the equation, this will get I equal to beta plus 1 into IB here. So, from these two equation alpha and beta, we will get, right, equation 2 and 3. If we substitute 2 and 3 into equation 1, we will get alpha equal to beta by beta plus 1. Similarly, beta equal to alpha by 1 minus alpha. Alpha is what? It is alpha DC, that is common base, okay, DC current gain, whereas beta is the common emitter DC current gain. Usually common emitter DC current gain is more, it is in the range of 40 to 50, whereas common base DC current gain is very low, it ranges from 0.9 to 0.998 here. And also we discussed about the both input characteristics and output characteristics of CC configuration. What is CC configuration? That is called as common collector configuration, where the collector acts as a common terminal between the input and the output here. When collector is common, therefore the base is the input and emitter acts as the output here. So, therefore, input characteristics, it is nothing but input voltage, that is VCB, versus input current, that is IB, keeping output voltage VC constant here. So, what you can note on from this is totally, right, the input characteristics of CC configuration are totally different from that of either CB or common base or common emitter configuration. And another point you can note on that, whenever the VCB increases, okay, What is VCB there? Okay. So, VCB increases, VBE decreases, and decrease in VBE will cause the base current to decrease. Therefore, we will get this type of characteristics, and it can be noted from this output characteristics what we discussed. There are three regions. One is cutoff region, active region, and saturation region. The region below the IB equal to 0 microamperes, that is the cutoff region, and the region below to the left of the VCE equal to 0, that is the saturation region, and the region between that of the saturation and cutoff region is called as the active region here. So, please note that for here once again, whenever the VCE increases, the IE will also increase here, because what is VCE? VCE is nothing but VCB plus VBE here. So, when VC increases, the reverse bias across the collector junction increases. So, when reverse bias collector junction increases, the depletion region width across the collector junction increases. So, that will reduce the distance between the depletion region that exists across the emitter junction and collector junction, and therefore, the collector current increases. Collector current is nothing but emitter current. So, therefore, emitter current will also increase here. So, finally, what you conclude, the common collector configuration is being used as impedance matching device. It is only because of the reason that it is having high input impedance and low output impedance here, and whereas common emitter configuration, it is being preferred as the amplifier. It is only because of the reason that it is having that high voltage gain and the low the high voltage gain, that is moderate voltage gain and moderate current gain here. That is all. Thank you. సరే అయితలా